I just want to introduce Mr. Mike Strois with AZZ Galvanizing out of Canton, and he's going to talk about continuous galvanized rebar.
Thanks to Billy and the Southeast Bridge Preservation Partnership for allowing me to do this. Something I've been working on for the better part of a year and a half. It's a little bit innovative and a little bit different for our field. I'll go through it briefly at the end if you have questions about the, I think on your sheet it says Duplex coatings or Metalizing. Whether you can see Kevin or I, you can talk to us about that or ask questions afterwards as well. So continuous galvanized rebar is a fairly new process. It's been 3 plants in the world, including one in the United States here for AZZ, and I'll say no more advertising after that, but one's in Xiamen, China, and the other one's in Dubai. So we feel like it's a worthwhile opportunity to discuss this and present it to you, and we've been around discussing this with states and different shows over the last year and a half, so we're excited to show you this. We're all familiar with the corrosion model of chlorides and carbon dioxide and water and air, and how it causes the stress and cracking in concrete. And the various states of iron oxide cause that cracking, and as you can see in this picture here, and you probably see it in your own states and other areas, that it's unsightly, it's unfortunate, but in this particular example, the galvanized handrail above it's performing well in the same environment, and in concrete it performs well too. And there's a couple different ways that it does that. Most of us are familiar with the hot dip galvanized, the traditional galvanizing A767. This is a case history going back to 1973 in Pennsylvania that's performing well still to this day. Jesup Bridge and the new New York Bridge, the Tappan Zee Bridge as some people call it, are pushing for 100-year design lives. Whether they get that, time will tell, but that was the intent of these bridges for a long life. And even in the Canadian provinces, Montreal, Vancouver, BC rather, and Ontario, they're using galvanized as traditional hot dip galvanized, and in this case in Montreal, they're even using it as a CRP installation. So looking at the National Bridge Inventory gets thrown in your face every day, I understand, but I'm just going to go through some quick stuff. We know how many bridges there are. The majority of them don't have protection. A lot of epoxy out there is what's available, and availability is definitely one of the key features for the product. Certainly galvanizing is out there in more than 41 states, and there's some polymers out there as well, and even cathodic protection. But add that all together, and this is the key part of what I want to present, is that less than 15% of that is corrosion protecting of all the reinforcements. So it's a pretty small amount of material out there. So we want to bring a little bit different approach to it, bring more availability and a dedicated process. So I'm part of a national task force group that talks about zinc coatings, and they're using concrete. Newer side is continuous galvanized rebar. So what is it? You've seen in the exhibits a bender, so it is a formable product. And you see that it's a continuous quality product that provides these things, durable, flexible zinc coating. That's an awesome benefit. You can fabricate this product at any time after the process. Pure zinc layer, which increases the corrosion threshold while keeping the great advantages of zinc coating, but it's at a reduced cost, and I'll go over some of these steps as we go forward. A little bit about the process. Typical lines can have up to 9 strands, but you're going to take the uncoated bars, you're going to have a surface prep where it's a near white, you're going to flux that, which prevents it from further oxidizing, preheat it, and then with induction, so it's rapidly heated, and any strength can be galvanized, or any existing rebar can be galvanized, and then it stays on the same plane and goes through a zinc trough. An air knife defines it, so there's no sharp edges, and it's formable. But this is the process. At this point, it's already fluxed, and it's going through the induction heater. As you can see, it stays on the same plane, goes through these guide tubes, the rolls are pushing it forward. The zinc trough that you see the zinc pouring out gets pumped up to the center, comes out both ends. So the rebar is passing through this against the grain on this side and with the grain on the other side. It goes through an air knife. That air knife is really just trying to define it and make sure that there's an even coating on top and bottom. It will roll a little bit through that, but the different guide rolls that skewed rolls don't help it really, so it's just regular guide rolls. In this case, they're water quenching it before they passivate it, and that's it. That's a 3-strand line in Dubai. China has a 7-strand, and they're widening it to a 9-strand. In U.S. here, we'll go up to a 9-strand line. Essentially, the process speeds, you can do a truckload in an hour. Very comparable to the epoxy producers and the speed, but it's dedicated to rebar. Coating thickness-wise, we're looking at 50 microns or 2 mils, but that's pure zinc. It's a little bit different than zinc iron alloy, the traditional, what you see in atmospheric or bridge applications or regular A767 rebar. There's 2 types in A767, type 1 and type 2. You have the bendable, which is a lower grade, and the unbendable, which is a heavier thickness. But when you compare it to the bendable grade, we're looking at the same corrosion resistance because it's pure zinc. Pure zinc is more corrosion resistant than zinc iron alloy. Here's a study by Tan and Hansen at the bottom here that's showing you an annealed surface is going to lose more in the initial pouring of concrete versus pure zinc. There's other studies that I can talk to you about individually that are currently out and more coming to also demonstrate this as well. So anyway, you have a faster passivation and a slower corrosion rate with a thinner coating. This is a photomicrograph of what the coating looks like. It's pretty boring, but essentially it's a zinc layer, all zinc. None of those spikes and zinc drawing to or iron drawing to the surface. Just have a ternary layer at the surface of the bar, which is iron aluminum zincate. That 0.25% aluminum that's in the zinc alloy is enough to suppress the inner metallics from growing to the surface. And that's what can make bending difficult on the traditional bar. So its formability, obviously you saw a bender in over there, but it's also formable with an epoxy overlay. So epoxy is definitely formable, but even with a coating on top of the zinc, it will follow. And here's another video showing the bending in what you'd have a traditional fab shop using, a high production fab shop using. So it's a Schnell bender, and they're using long lengths of bar in different shapes, a 90, a 180, and in this case, a circle. So when they use these bars, in this particular example, there's no protective rolls in this. So it's a knurled teeth. I'm not sure if you've ever seen a former, but these teeth down here, they grab onto this bar and they spin it around. For epoxy and some other coated products, you have to use a plastic roll. So you can use either to do it, but it just gives them a little bit more speed and process to do it this way without any issues to the bar. So how is CGR, and even this works for galvanizing too, how it protects the bar? CGR has some advantages over the hot dip for the protective reaction. It forms a calcium hydroxyzincate. That's what the CAH at the end is. And it's a high chloride threshold, 2 to 4 times, which I'll show you in the next slide, low pH tolerance, carbonation, and corrosion product migration, as well as a barrier coating. So you have a galvanized, which is a coating, obviously, and because it's a metallurgical bond, and a zinc metallurgical bond, you're also providing cathodic protection. This service life model shows, it's a condensed model, essentially stress over time, shows you that when uncoated bar, you saw it in this, the initial slide where it creates that stress and causes cracking, you're going to get 2 to 4 more times chloride protection. The reason why it's 2 to 4 times is you have different studies out there. 2 to 4 times shows Some of the studies were, was the hot dip galvanized that didn't form an ADA layer versus a continuous, which is all pure zinc. So you're going to get a different passivation model in continuous versus hot dip. Hopefully in hot dip, if they do it well, and there's guys out there that do hot dip excellent, and they can form the ADA layer, which is the pure zinc layer on the outside, that gives you more chloride profile at that. But in any case, it's protecting it and surviving over time. So how zinc passivates in alkaline concrete? So like I said, it forms a calcium hydroxyzincate. In atmospheric conditions, and galvanizing performs very well in atmospheric conditions, it forms a patina. In wet concrete, it forms a calcium hydroxyzincate. So that's it's almost a crystallized layer, and as it slowly corrodes, it's very microscopic and actually will migrate through the pores of the concrete. But that protective film, it creates when it's attacked, it appears, and it resides. So it commences immediately when concrete's poured, but as it cures, it dissipates. So that's basically what it says in all these little bullet points here. Load slip, and again, there's more studies underway. These are existing studies from Tannen Hansen, University of California, that shows that galvanized rebar will perform equal to black or better, but definitely better than epoxy. Depending on the characteristics of the traditional hot dip galvanizing, you had some variability in how it does. But because we're able to, in the new process, have a repeatable product with pure zinc, you'll see that future studies will show galvanized will perform better than black. That doesn't mean you change your lap lengths or anything like that. It just means you're going to have great slip resistance and use it comparable to use it how you would in uncoated. Bond strength is going to be excellent as well. With these studies, this is University of California study showing that it basically has an excellent bond strength, better than black or uncoated. This is a little bit different slide. When possible, you've used reference electrodes to attach it to galvanized and even an uncoated steel, and you measure how it's performing. And on the left, you see C876, which is the ASTM study that shows a probability of corrosion. So if it's less than 200, you have a low probability, and on the higher end, it has a high probability. Well, those numbers are skewed and don't read how zinc corrodes, which is a little bit different. So we're working through this, but two studies we've showed with the University of Waterloo and an NRC study, which is on 11 bridges in Canada, are showing that there's a difference, a very wide difference. So you could look at readings for galvanized, and it'll actually show that it could be in the high probability of corrosion, right, where it could be actually performing well. So we're working through that and trying to talk to ASTM C876 and see where we can get a little bit of difference, but I'm sure that's going to take future studies. So insulation, treat it just like regular uncoated bar. The only thing you'll need to do is worry about the ends. And with our model, what we're looking at is long lengths of bar that is going to be processed in the fab shops. So they'll touch it up there. Once it gets into the field, your coated ends or your cut ends should be repaired. Obviously, you have to check it, but you won't have to worry about damage to the coating because it's a very, very durable coating, and you won't be able to just drop it and roll it around and chip the coating off. It's way too durable for that. You got a very good bond to the steel. But same overlap lengths as uncoated and handling procedures. There's no UV or weather restrictions in the coating at all. For connectors, we'd recommend using, if you're using galvanized, you'd use galvanized or plastic. So a little bit about pricing and comparison, and it's regional, but this is based on data through the United States and what's been published out there. So if you have uncoated bar, epoxy is usually a premium of 40 to 50%, maybe even lower. It depends on where you are in the region. Galvanized is probably a little higher. That's traditional hot dip galvanized. In some regions in the Northeast, it's extremely, it's much lower than that. But as an average across the United States, it's very comparable. And again, regionality. But MFX is pretty consistent for where it is. It's more than 3 times, and stainless is more than 6 times.
Where the continuous process comes in with automation and coatings, a little bit lesser of a zinc coating, it's going to come in very comparable to the epoxy and very competitive. There's not much regionality, obviously, because there's not a lot of plants yet, but we believe in the next, probably in the next 2 years, you'll have as many as 6 plants from other vendors. So ASTM specifications, 1094 has been out for 3 years, going on its 4th. And A1055 has also been out there. A1055 was traditionally known as the Rebar specification, a metalized system with a dual coat over top. Now allows type 2 for continuous grade galvanizing. So you've got to have an epoxy producer take the current continuous galvanized and coat over top of it. First location in the United States is in the near the Tulsa area. But again, I believe in the next 2 years you'll have as many as 4 to 6 and throughout the country. There's been a couple installations. Small Bridge in Canton, Ohio, basically used it for their abutments. Pretty small installation based on the samples that we had. And also in near the Tulsa area, Port of Catoosa, for some foundation work. That's based on with samples. Future production, obviously we have some production lined up for other products.
Thank you, Ed. Quick question over here. I'm going to give a little history because then you'll find out why I'm asking this question.
Okay.
I started working for Florida Department of Transportation in 1994. Previous to that, they'd used epoxy-coated rebar, and they had some issues with it because they apparently weren't either really good at coating their ends, you know, when they got cut, or taking care of nicks and stuff like that. So they ended up setting up a corrosion cell, and I guess that the nicked areas acted as an anode and started sacrificing itself, and they had a lot of corrosion. And they decided to move in a different direction. What they did was they tried to experiment with, I think it was calcium nitrate in the deck slabs, and that hasn't worked as well as it could. You know, where they were thin, and in substructures they went to thicker cover, and they started using silica fume to try to densify it, which worked better, but you can't do that in a deck. My question is this. You said you recoat your ends, but because it's galvanizing, it would seem to me, since that's a sacrificial material to begin with, it probably wouldn't be anywhere near as critical if you did have a neck over there, because it would just mean you'd start sacrificing a little bit early, and we'd still have to sacrifice a lot before you'd actually start losing the actual steel. Is that the way you understand it too?
Thanks for pointing that out, but that's very accurate. And you know, there's continuous different types of products out there, whether it's Gabion mesh or continuous wire or guardrail, or a continuous grade of guardrail that they have punched holes and stuff. But where you can, obviously you want to try to repair it to minimize it as much as possible. You're there, get it done, no problem. But that's why we're trying to say that. We don't want to, and on our end, we'd rather say touch it up and not have to worry about anything else, because you're not going to have to worry about the field damage or anything like that to the typical coating. So repair the ends and we don't have to worry about it. I know if you don't, it's going to sit in the field. You're going to see a little bit of orange staining in the end down the road, and someone's going to point it out. But you are going to have sacrificial protection from their surrounding zinc.
Another question on the development links. It looked like the development links were for hot dipped. It was not for the continuous.
The first model is, and that's based on a study that's been out there for a while. But with the continuous process, you're going to have a pure zinc layer, similar to the tests that were done with it, which were determined on an ADA layer, which is a very similar. We have some studies with the University of Akron and Ohio. They're almost done or done, and initial readings are very comparable, if not better. And they're
Okay, so there is research being done on this particular thing. Also, with kind of looking at the process that you were showing there in the video, is there any difficulties with larger bars?
The first systems in the U.S., let's say, would be able to do number 3 up to number 10 bar. Not a lot of bending on above 10, number 10. But future lines will have the capability to look at larger diameters for some potential for if people are interested in dowels. But the first line, the guide tubes are just a little too small to go beyond that. A typical length would be, the mills are producing up to 60 foot, so they would send 60-foot material in, run that through. We can go down to 20 if it's necessary, but. Yeah. Anything else? Thank you very much.